All right, welcome back to another calculus lecture. So in today's lecture, what I want to do is just walk you through a few different computations, a few different calculations with definite and indefinite integrals. So these are going to involve how to do some certain Usubstitutions, how to compute these definite integrals using the fundamental theorem of calculus, things like this, so that when you encounter these integrals in quizzes and in your homework, it's not too much of a mystery of how to actually do these calculations. Okay, so I'm going to do 5 examples today that are hopefully representative of the kind of calculations that we typically do in this course. So the first of these, so let's do one. Compute the integral from 0 to pi of e to the x plus secant squared of x dx. Okay, so this one is just a pretty simple integral calculation. There's no Usubstitution that needs to happen because we know the antiderivatives of each of these two functions. So this integral is going to be equal to, we'll just go ahead and write it on this new line. So we know that the integral is linear, so we can split it apart into two integrals. This is the integral from 0 to pi of e to the x dx. And it's not sort of necessary to show this much work when you're doing integral computations. I just want to make sure that every step is sort of clear. 0 to pi of secant squared of x dx. And then we can compute the antiderivative of each of these functions. So this is going to be, the antiderivative of e to the x, or one of the antiderivatives, I should say, is e to the x. We're gonna, the little constant that we should add on, we're just going to treat that as 0 because we're doing a definite integral, and we can certainly do that because any antiderivative works for the fundamental theorem of calculus. So we have e to the x, and then the antiderivative of secant squared is tangent. So this is going to be plus tangent of x, and then we're going to evaluate this from 0 to pi. And remember what this notation means. It just means plug in the upper value, plug in the lower value, and then subtract. So we get e to the pi plus tangent of pi minus e to the 0 plus tangent of 0. And this is equal to, well, e to the pi is just e to the pi. It's a number. You could put this in a calculator and get a decimal approximation. Tangent of pi is 0 because it's sine of pi over cosine of pi, and sine of pi is just 0. Minus e to the 0 is just 1, and then I have a minus tangent of 0, but tangent of 0 is also 0. So this is just e to the pi minus 1. And if we were putting this in on a computer or something, we could get a decimal approximation for it. And that's it. So we're all done with that one. So the next one is, this will sort of demonstrate one of the properties that we looked at previously with the integral. So, whoops, I don't want to go from 0. I was looking at the previous problem. So I want to go from -3 to 3 of x cubed minus 2x dx. Now, from lecture, we know that this function right here is an odd function, and this interval right here, -3 to 3, is a symmetric integral, or interval. That's really easy to confuse, and so I'm probably going to do that a few more times. But this interval, -3 to 3, is symmetric about the point 0, and so this integral should just come out to be 0, right? If I integrate an odd function over a symmetric interval, goodness my, then I should get 0. That was one of the things that we looked at. So let's go ahead and see how that actually plays out. So no need, we'll actually just do this on the same line and not, rewrite the integral. So the antiderivative of x to the third, I'm going to abbreviate some steps now. So the antiderivative of x to the third is just 1/4 x to the fourth. Remember, with the power rule, I take the exponent, I add 1, and then I divide by my new exponent. So here I have x to the 4, and I divide by 4. Same thing here, I have x, that's going to go up to x squared, and then I divide by 2, and that's going to cancel with this 2, so I just get x squared here. And this I want to evaluate from -3 to 3. Well, let's plug in 3 and -3, so this is going to be 1/4 3 to the 4 minus 3 squared, and then minus, so that was evaluating the upper limit, and then we'll evaluate the lower limit. Here we put in -3 to the 4 minus -3 squared. And then we notice that because these exponents are even, the negative here doesn't matter. If I take a negative number and I raise it to an even power, then really I'm just squaring it and then exponentiating the new result of that a few more times. So this is the same thing as just putting in a +3. And so we'll just go ahead and write down the step for that. So this part doesn't change. So the negative goes away in both of these because the exponent is even, and then I don't even have to compute this, what this number is, to know that I get 0 at the end. Okay? So this is a specific example of how the integral of an odd function over a symmetric interval vanishes. It's 0 when you actually perform the integration, and it's because these odd functions, when you integrate them, you're going to get an even function back out. At least that's what happens with odd powers of odd powers of x, and polynomials that consist only of odd powers of x. Okay, so there's that one. Let's do maybe a computation with the second fundamental theorem of calculus. So let's do compute, and we'll do a little bit kind of different computation than we've seen before. So let's compute the derivative of the integral from 1 to x squared of natural log of t sine of t dt. Well, when we looked at the second fundamental theorem of calculus before, or sort of part 2 of the fundamental theorem of calculus, there was only an x up here. We didn't have another function. It wasn't, some power of x. It wasn't anything other than just x by itself. So how do I actually treat this? Well, the point is that we use the chain rule here. So we view this integral as a function of x. So when I differentiate this function of x, I have to differentiate the thing inside of that function. So you can think of this whole integral. So we can think of f of x equal to the integral from 1 to x of the natural log of t sine of t dt. So we are computing, so again, I'm viewing this integral here with this upper limit as a function of that upper limit. So we are really computing the derivative of f of x squared, right? I'm just taking this integral and I'm plugging in x squared for that upper limit. Well, if I want to compute this derivative, I'm going to have to apply the chain rule because I have a composition right here. So thus, the derivative of this integral from 1 to x squared of the natural log of t sine of t. Notice I chose an integral that we clearly cannot integrate. We can integrate individually natural log and sine of t, but their product is not, we don't really know how to do that. So this is really just the derivative of capital F of x squared. And this we differentiate using the chain rule. So this is going to be f prime of x squared times the derivative of the thing we're plugging in. So remember, the chain rule says we differentiate the outside function, we plug in the inside function, and then we multiply by the derivative of the inside function. Well, f prime of x was this thing, and that I know how to differentiate. That we can do just with the usual Fundamental Theorem of Calculus Part 2. That just gives me this integrand right here evaluated at the point x. So this is going to be natural log of x, sine of x, squared, I should say, because we're actually plugging in that x squared. Once we differentiate this, we do need to actually plug in x squared, and then we multiply by 2x. Okay? So all that's happening here is just a more elaborate setup of the chain rule. Nothing too exciting, but all you do is simply plug in the upper limit of integration, this x squared or whatever function you have, but then once you've done that, you multiply by the derivative of it, because the chain rule tells you that that's what you need to do. Okay? So that's how you can do these fundamental theorem of calculus problems, differentiating integrals, but maybe where the limit of integration is not necessarily just the variable x. It might be some function of x. No problem there. So let's do a few Usubstitution problems, and then we'll call it good for this video. So let's compute the integral from 2 to 4 of x times the square root of x plus 2 dx. Whoops, I meant -2, and I'm going to go up to 14. Misread my notes in writing that integral. So I want to compute this integral, and again, I sort of am faced with, I have this x outside, I know how to integrate that, I know how to integrate x plus 2, and even if I just had x plus 2 by itself, maybe I could do a change of variables and switch up this square root to make this integral actually computable. Well, what exactly do? I don't know exactly how to attack this integral. Let's try a Usubstitution, even though if I look at this, and our philosophy for the Usubstitution was I look for a function which is inside of another function and whose derivative appears somewhere else in the integral. Well, the only composition I have is the square root, and I have an x plus 2 inside, so I guess that's my only candidate, but then its derivative doesn't really appear anywhere else. Its derivative is just 1, so it sort of trivially appears, but not in the usual sense that we think of it. Well, let's go ahead and try and do a Usubstitution and see what happens. So we'll let u be this x plus 2, and then the new differential is, well, derivative of u with respect to x is just dx, or du dx is 1, and then you can think of multiplying by the dx over. Again, we're computing differentials, so that's not quite right to say, but at least it works with the notation that we have. So I've got my new differential, that's my dx, and I've got this x plus 2. Well, what do I do with this x? Well, notice that I can actually just solve for x in this equation right here. So x is equal to, let's just subtract 2 from each side. X is u minus 2. Simple enough. And while we're at it, why don't we go ahead and get our new limits of integration. So u of -2 is equal to, well, I add 2, so this is -2 plus 2, which is 0. And u of 14 is 14 plus 2, which is 16. And now, let's go ahead and just rewrite the integral using all of this new information. So, the integral from -2 to 14 of x times the square root of x plus 2 dx, this is equal to, I change my limits of integration from -2 becomes 0 and 14 becomes 16. X becomes u minus 2, and then x plus 2 just becomes u. So, and I'll go ahead and write that as u to the 1/2 because I want to apply the power rule. Now, again, I have a product of two functions, but notice what I can actually do here. I can actually just distribute this u to the 1/2 to each of these, and I end up with a power of u. So this is the integral from 0 to 16. U times u to the 1/2 is u to the power of 1 times u to the power of 1/2, and 1 plus 1/2 is 3/2. So this is u to the 3/2 minus 2u to the 1/2 du. And now I'm in a place where I can apply the power rule. So this is equal to, I add 1 to each of these exponents, and I divide by those new exponents. So 3 halves plus 1 is 5 halves, and when I divide by 5 halves, I get 2 fifths. So this is 2 fifths u to the 5 halves, and then minus 2, 1 half plus 1 is 3 halves, so I divide by 3 halves and get 2 thirds, u to the 3 halves, evaluated on 0 to 16. And we might as well just go ahead and compute this. At this point, you can just plug it in a calculator and get a number out, but this will be 2 fifths, 16 to the power of 5 halves, minus 2 times 2 thirds, times 16 to the 3 halves, minus, same thing, but we just plug in 0. And, you know, if I plug in 0 to each of these, you can see that I'm actually just going to get 0, so I won't bother writing that step down. So this is just minus 0, because each of these is just clearly 0 when I plug that in. So this we can actually compute, so this is going to be 2 fifths, the square root of 16 is 4, so this is 4 to the 5th. Square root of 16 is 4 to the 3rd now, so minus 2 times 2 thirds is 4 thirds. This is 4 to the 3rd. And if I was a better instructor, I would have actually computed that as a number. I'm not going to try and do that in my head because it's a little bit, the numbers are a little bit too big and I don't know my powers. This is something. Good job. Anyway, so you can get what this number is if you actually put it in a calculator. But the point of this is to show that sometimes when we do a Usubstitution, we may not have exactly just the derivative appearing in the integral. We may have some other stuff, but that doesn't mean that we can't actually evaluate the integral. Sometimes we have to do a little bit of work with rewriting our variable x in terms of this new variable so that we can sort of switch things around. The point is that these two integrals are morally the same object. You know, I've sort of switched around the symbols that I've written, but really I'm just doing the same thing. And you can think about x plus 2, it's really just the graph of x, but shifted up by 2. And so when we do this change of variables, all we're doing is actually just sort of shifting graphs around and correcting things so that we can apply the techniques that we have for the integral to this new expression. Okay? So one more integral, and then we'll go ahead and be done. So let's just compute a general antiderivative. So let's compute natural log of x divided by x dx. Well, this is, you know, I know how to compute the antiderivative of 1 over x, but I don't quite know how to compute the antiderivative of the natural log of x. So how do we go about doing that? Well, here we're going to do another Usubstitution. So I look for a function. Here I don't really have any compositions of functions, but I do have a function whose derivative appears elsewhere in the integral. And if you sort of don't see that right away, it might be helpful to pause the video and try and figure that out for yourself. What's the function whose derivative appears elsewhere? So that function here is actually the natural log of x. So the natural log of x, its derivative is 1 over x, and so we can use the method of Usubstitution to compute this general antiderivative. So let's let u equal natural log of x, and du, the new differential, is going to be, well, I differentiate natural log of x and then multiply by dx. So I'm going to have dx divided by x. So there's my 1 over x times dx. And now this new integral, this is equal to, well, what is this? Natural log of x is just u, du is, or this dx over x became my du, so I really just have u times du, and that's it. Well, that's certainly easy to compute the antiderivative of. I just apply the power rule. But I'm computing a general antiderivative, so I need to add my constant c in there. And then, now that I've done this, all I need to do is replace my u with its definition, because we want to have our final answer in terms of x. So this is going to be 1/2 times the natural log of x squared plus c. Okay? So that's how we can do general antiderivatives using the chain rule, and sometimes the chain rule, or not the chain rule, the method of Usubstitution. I get them confused because one is just the other in reverse. But we can use the method of Usubstitution to compute these general antiderivatives, even though we don't quite have a composition. You can think of the sort of 1 over x as natural log of x is inside of that, as in it's inside of the numerator of that. But you sort of need to think for a moment sometimes with these Usubstitution problems in order to figure out how to compute these integrals. Okay? So that's everything for this video. I just wanted to do a few calculations so that when you are asked to do these, when I ask you to do them in your homework and on the quizzes, it's not unfamiliar to you, or at least you have some sort of reference for how to do these kinds of calculations. Okay? So I'll see you all in the next lecture.